Hi everyone, I'm back again. This is chapter 1.2a, Name That Real Number. So this is following up on chapter 1.1, Types of Numbers, Natural Numbers, or Counting Numbers. N equals 1, 2, 3, 4, 5, 6. Whole numbers. The number 0 is added to the set of natural numbers, so it's just the counting numbers with 0 added. That's designated by the double bar W. And of course, numbers inside of these curly braces is called a set. So this is a set of whole numbers. Integers are designated by a double bar Z. Z equals the set of -4, -3, -2, -1, 0, 1, 2, 3, 4. The integers are one of the most important stepping stones from arithmetic to algebra, since the concept of positive and negative numbers is basic to algebra. Integers can be represented on a number line by marking 0 at some point and then marking the positive integers to the right of 0 and their opposites, or negative integers, to the left of 0. So as you can see, we have 0 in the middle, negative numbers to the left, positive numbers to the right. This is just a regular number line here on the x-axis. Numbers that can be written as fractions and whose numbers are integers and denominators are non-zero integers have a technical name: rational numbers. Integers and terminating and infinite repeating decimals can also be classified as rational numbers. For example, the following numbers are all rational numbers. Rational numbers can be written as two integers over top of one another, as seen here. So we have 1.3 equals 13 over 10, 5 equals 5 over 1. Any number in algebra can be written as that number over 1. -4 equals -4 over 1. We see that example right here. 3 over 8 and 2.8333 equals 17.6. Variables are needed to be able to state rules and definitions in general forms. The definition is restated here for easy reference and for emphasis. A variable is a symbol, generally a letter of the alphabet. The most commonly used variable letter is X, but they can be any number. X and Y are the two most common ones, X, Y, and Z. That is used to represent an unknown number or any one of several numbers. The variables A and B are used to represent integers in the following definition of a rational number. A rational number is any number that can be written in the form A over B, where A and B are integers and B is not equal to 0. The letter double bar Q represents the set of all rational numbers. So I'm going to go ahead and skip this rational number example because I've already given you some examples, but feel free to pause this video and read over that. Rational numbers have been defined as numbers that can be written in the form A over B, where A and B are integers and B is equal to 0. With this definition, we can show that in decimal form a rational number is either a terminating decimal or an infinite repeating decimal. Examples of terminating decimals are 1 over 4 equals 0.25, 3 over 8 equals 0.375, and so forth. Irrational numbers. The following are irrational numbers. Note that there is no repeating pattern in their decimal representation. The 3 dots indicate that the digits continue indefinitely. So as we all know, pi is an irrational number because it does not end, it is infinite. Pi has no repeating pattern in its decimal form. Also, it has no repeating pattern. The square root of 2 has no repeating pattern in its decimal form. E is a number used in higher mathematics and engineering courses. As you can see, it's infinite and it doesn't repeat. Even though there is no pattern to the digits, the pattern is not repeating. Here we have a little bit of a tree example. Together, the rational numbers and irrational numbers form the set of real numbers. The relationships between the various types of real numbers can be seen in the diagram. So real numbers anything. That breaks down to irrational and rational numbers, non-integer rational numbers, integers, negative integers, whole numbers, zero, and natural numbers. Understanding these relationships is critical for success in algebra. For example, if a problem calls for integer solutions and your solution is 3/5, you need to understand that you have not found an integer solution. Property. Summary of relationships among various types of numbers. Every natural number is also a whole number, an integer, a rational number, and a whole number. Every whole number is also an integer, a rational number, and a real number. Every integer is also a rational number and a real number. Every rational number is also a real number. Every irrational number is also a real number. Given the set -3, 1/2, 4, square root of 10, tell what classification each number fits. As we can see, the solution is -3, integer, rational number, real number, 1/2, rational number, real number, 4, natural number, whole number, integer, rational number, and real number, square root of 10, irrational number, real number. All numbers are real numbers. Again, this is just given the set of real numbers, tell which numbers are integers. You can feel free to pause the video and complete that if you would like. Real number lines. There is a one-to-one correspondence between the real numbers and the points on the line. Thus, number lines are also called real number lines, and every rational and irrational number has a corresponding point on a real number line. Graphing real numbers. Let's skip this. Sets and set builder notation. A set is a collection of objects or numbers. The items in the set are called elements, and the sets are indicated with braces and named with capital letters. If the elements are listed within the braces, as we have done earlier with the set of natural numbers N, the set of whole numbers W, and the set of integers Z, the set is said to be in roster form. The symbol, this looks like an E, is red, is an element of, and is used to indicate that a particular number belongs to a set. For example, 0 is an element of the set of whole numbers, and -3 is an element of Z, Z being the set of integers. If the solution in a set can be counted, the set is said to be finite. If the elements cannot be counted, as for natural numbers, whole numbers, and integers, the set is said to be infinite. If a set has absolutely no elements, it is called the empty set or null set, and is written in the form brackets with nothing inside of them, or with a special symbol, circle with a line through it. For example, the set of all people over 12 feet tall is the empty set. The notation, brackets, x with a line in front of the x is read the set of all x such that, and it's called set builder notation. The vertical bar is read such that a statement following the bar gives a condition or restriction for the variable x. For example, x such that x is an even integer is read the set of all x such that x is an even integer. Here we have x such that x is an element of integers, or an element of the set of integers. Is read the set of all x such that x is an element of the set of integers. The following inequality symbols can be used to indicate relationships between numbers, and along with set notation to indicate entire sets of real numbers. Here we have inequality symbols. We will get into these later. But here we have less than. So to use this symbol, there would be a number here on the right. So say 40, and then 39 would be on the left. So 39 is less than 40. And a trick that my elementary school teacher told me is that for less than, think of the inequality symbol as an alligator's mouth. It eats the bigger number. And of course we have greater than here is just that sign, but it's flipped. Less than or equal to, the symbol is the same, except it has a horizontal line underneath it. And then the same thing for greater than or equal to. Looks like the greater than sign with a horizontal line underneath of it. Using set notation and graphs to indicate sets of real numbers. Set notation. So x such that x is less than or equal to a. Here we have the graph. These are two different ways to indicate that. This is a number line demonstrating a closed interval. This is a number line demonstrating, once again, a closed interval. And here we have x such that x is greater than or equal to b. Again, the dot in the bracket like this will be a closed interval, and parentheses and an open dot here will be open intervals. Here we have x such that x is less than a or x is greater than b. The set of all x such that x is less than a or x is greater than b. So here we have the part of the number line demonstrating that there's two open intervals right here. So x is less than a, or x is greater than b. Again, we have that demonstrated here with the two different types of notation. And as you can see, for the or word here, the or and are important because they determine the type of graph that you're going to have here. So x such that x is greater than a and x is less than b. So right here we have x is greater than a, so it's going to be greater than a, and x is less than b, so x is going to be less than b. So x is somewhere in here. This is also known as the intersection of two sets of numbers. The concepts of union and intersection are part of set theory, which is very useful in a variety of courses, including abstract algebra, probability, and statistics. These concepts are also used in analyzing inequalities and analyzing relationships among sets in general. The union symbolized U, as in A union B, of two or more sets is the set of all elements that belong to either one set or the other set, or to both sets. The intersection symbol symbolizes an upside down U, as in A intersect B, of two or more sets is the set of all elements that belong to both sets. The word or is used to indicate union, and the word and is used to indicate intersection. For example, if A equals 1, 2, 3, and B equals 2, 3, 4, then the numbers that belong to A or B is the set A union B equals 1, 2, 3, 4. So the sets are combined, but not repeated. The set of numbers that belong to A and B is the set A intersect B, which is 2 and 3, which means that both sets are looked at and the numbers that are not in both sets are excluded. These relationships can be illustrated using the following Venn diagram. Similarly, union and intersection notation can be used for sets with inequalities. For example, it's x such that x is less than a or x is greater than b can be written in the form x such that x is less than a, union x such that x is greater than b. Also, x such that x is greater than a and x is less than b can be written in the form x such that x is greater than a, intersect x such that x is less than b, or x such that a is less than x is greater than a, or x is less than b. Graphs indicated by inequalities. graph the set of real numbers x such that x is greater than or equal to negative 1. X is less than 2. So right here, we see that there's a mixture of an open set and a closed set. Okay. So we have the negative 1, because the x here is greater than or equal to negative 1. So that means the negative 1 is included in this, because it's greater than or equal to negative 1. X is less than 2. So the 2 is not included here. So the next would be 1.99. That number is included, but 2 is not included. Graph the set x such that x is greater than 3. As you can see here, 3 is not included, but 3.1 is included. But it starts at 3, so you still have to graph the 3. That's where the notation differences come in. In example 16, note carefully that the use of the word and to indicate intersection. In example 6d, the use of the word or to indicate union. And again, this is more graphing here. So x, graph the set x such that x is less than or equal to 2 and x is greater than or equal to 0. The word and implies these values of x satisfy both inequalities. The solution graph shows the intersection of the first two graphs. So these are graphed independently at first, and then they are combined here. So x is less than or equal to 2, and x is less than or equal to 0. So there we have the graph for that. And you can feel free to pause and take a look at the last graph for yourself. Thank you, and looks like our next lesson is going to be chapter 1.2b, properties of real numbers. Thank you again.